Good morning. So today we have the class about Fraunhofer diffraction due to a circular aperture. Okay. So in the previous class we have seen about the Fraunhofer diffraction due to the single slit and its central maxima, minima, everything we have shown for the single slit. Now today is the session about the Fraunhofer diffraction due to a circular aperture. We are just removing the single slit and replacing with the circular aperture. Okay. Now, so let us focus on the diagram. So what are the things are appearing here? We are using a wavefront, that is a W dash. W dash is a wavefront. Okay. Then all the wavefront is focusing towards the circular aperture AB with the diameter D, with the circular angle of diameter D. Then a lens is also constructed in between the screen and the circular aperture. Okay. Now, if the wavefront consists of a monochromatic light, okay, which consists of single wavelength, suppose let it be lambda. Now, according to the Huygens theory, every point in the wavefront makes the secondary wavelets as it is moved towards the circular aperture, or it focuses on the single slit. So, it forms the secondary wavelets. Now, as a light travels, as a wave travels from the wavefront from the right side to the towards the screen, then so the waves which are normal to the circular aperture, they will come across focus across the P naught. Okay, the waves which are normal to the circular aperture will be going to be formed at the forms at the point P naught, and the secondary wavelets which is traveling in direction corresponding to the inclined angle theta. Okay. So when the secondary wavelets traveling will be at inclined angle theta and normal to the aperture only, so then they come to focus at P1 on the screen. So let's suppose think that P0 and P1 is there on the screen. The distance between the P0 and P1, let it be x. Okay. So from the triangle like ABC, so from the triangle ABC we can draw that, or ACB we can draw that AC equal to AB sin theta, that is AB is nothing but D, so AC is equal to D sin theta. Okay, so this is from the diagram. Now when we compare these maximum intensity with the path difference, then so if the intensity is maximum, the path difference will be 2n plus 1 into lambda by 2, means odd multiples of lambda by 2, and if the intensity is a minimum, the path difference going to be exist is integral multiples of lambda, that is n lambda. So we can substitute the n is equal to 1 to 3 and so on. So as the circular aperture is going to be used in our instrument, okay, as the circular aperture is used, the diffraction pattern surrounded by the screen or the discs is known as, especially or the rings, is known as Airy disc or the Airy rings. Okay, suppose think that if a lens is placed near the aperture or away from the lens, okay, then sin theta is equal to x by f. Okay, sin theta is equal to x by f. Now substitute these equation 3 in the place of equation 2. What will get? We have the equation d of x by f is equal to n lambda. On the both the sides, the sin theta will be going to get cancelled. Suppose this is a formula. If we substitute as n is equal to 1, right? If n is equal to 1, x by f is equal to lambda by d. Then x is equal to f lambda by d, right? So finally we can conclude with the statement as x is equal to, x is the radius of the Airy disc. Okay, so as x is equal to f lambda by d into 1.22. So exact value of x, this is the exact value of the x. So what is the x value? The difference between the formal primary wavelet and the secondary wavelet P1 and P0 is x. So that x value will be 1.22 into f lambda by d. So this is a case of Fraunhofer diffraction due to the circular aperture. Okay.